So yeah, it's awesome to be following up on Sumner's talk. We'll keep going on brain-computer interfaces here, but now we'll focus a little bit more on the neurodecoding and how machine learning can be used for it. So a little bit about myself. My name is Diogo de Lucena. I'm a data scientist at AE, and my background is in rehabilitation robotics. I have a PhD at UC Irvine doing rehabilitation robotics for people that suffered a stroke or spinal cord injury. Uh, and that I was a postdoctoral fellow at Harvard, um, still doing rehabilitation robotics, but now soft robotics, always trying to find ways to help people that had some sort of paralysis or impairment to regain function and understand how those injuries really affect their brain and their daily lives, and trying to help with that. Um, so here we'll be focusing on neurodecoding with machine learning. Um, but to go through that, we'll start discussing a little bit what neurodecoding really is. And you, if you saw Sumner's talk, it's going to make sense that this is just one piece of that brain-computer interface system. Um, then we're going to look at how machine learning can actually help with that task, and specifically what we've been doing at AE with different projects that we've touched on, and other activities that we've been doing on the BCI field. Then we're going to conclude kind of reviewing everything, and just giving some thought about the future of what we'll be doing here at AE. So what is neurodecoding? So here we're really looking at it as a component of a brain-computer interface, right? So we have sensors that are measuring measuring brain activity when people are doing intention of movements or speech or trying to move a cursor or trying to write something. And we want to convert that into actions for a robot or for a software or for a computer. Uh, this conversion of intention of movement from neuroactivity into actual actions is not trivial, and that's what we're going to focus here. How can we decode those neuroactivities into actions? Uh, and the challenge with that is that neurodata is really complicated. It's not very easy to interpret by the naked eye, or it's hard to find patterns in it. A lot of it uh, is processed in the frequency domain, not in time domain. It's super variable, both for across different people and for the same person when they're trying during different days or different times of the day. The data is super variable. So deep learning really is a great tool to try to approach this. The amount of data produced by these different sensors, either if it's electrical, optical, whatever sensor we're using, it's really massive. So processing all of that quickly is really important for when we're trying to help people speak again or move again. This needs to be really fast. So deep learning is a great tool for that. And it is really state of the art of accuracy of how we can get those decodings happening in real time. But why are we doing this at AE? We really think that BCI may be the primary method of communication in a few years between people. We think it has so much impact in humanity for different applications, both communication, but also now it's mostly focused on trying to regain movement for people that have some sort of impairment. So it really it's in its infancy, but it's really powerful, and it's pretty clear already. And we want to make sure that whoever develops BCI helps increase human agency rather than decrease it. You can imagine how big tech companies could, or for example, social media companies could use this in a way that is not really helping people increase their agency and taking your thoughts um, into ways that are not really what you intend to use it. So we want to try to create this BCIOS in a way that we can take all these different kinds of sensors that can measure brain activity, uh, and create tools that people that are developing new BCI software or BCI applications can use them to facilitate the creation um, of new systems, but keeping the user uh, as the focus and prioritizing user agency, uh, privacy of data, letting the person that is using it decide when they want to use it and how they want it to use it. And we want to make sure that uh, it's an extension of the user thought and it's owned by the person. It's maybe even a little bit further than just privacy, but really that it's the self that is being represented in those thoughts and in this BCI application. So we think it's really important that whoever is leading it in a good way, and we think we can do that really well. So to get to that point, right now we're really starting to engage with experts in neuroscience, and we are becoming the experts in neurodecoding using deep learning. We have a an excellent team of data scientists that understand a lot about deep learning and great neuroscientists as well, helping us understand how to apply these deep learning techniques that we know so well to help with neurodecoding. And we're doing it with a variety of different types of sensors. So we're not focusing on one specific technology, but really trying to engage all different technologies and create something that can be used in a variety of ways. And the way that we do it right now is that we look at research, the most advanced research that is out there, and we take that original research, we take those data sets that they create and they share, we reproduce their data, we reproduce their results, and we improve on them. We create models that perform a little bit better. We create infrastructures that are easier to use. And with the goal of that is really to give it back to the community, to the neuroscience community, uh, tools that are easier to use, that then they don't require so much of a software development, but really just the neuroscience part, and the software development and the data science part we do as that is our expertise. And we do that by using a bunch of different tools that are out in the market and really putting them to good use. So to discuss a little bit on how we do this, I'm going to go over a few examples of what we've done in the past. For instance, this project is in speech decoding with ECOG. So ECOG is short for electrocorticography. And maybe a lot of you are more familiar with EEG, so those electrodes that you put in your head to measure brain activity. But they're really difficult to use because you have your skull, your scalp, and all of that signal is really mixed together, and it's really hard to interpret. ECOG is placed right on top of the brain, on the cortex, where all those neurons are really activating, and it's much easier to differentiate signal from different sensors. And it's really an array with a variety of positions, and for each of those positions, we measure activity of neurons in that region. Here's an example of what that data looks like. So on the left here, you see data from several channels, which are electrodes, and their voltage varying across time. Here's a little bit of, in the middle, you see a zoom in one of those signals. But in reality, interpreting those the raw voltage is really difficult. So what we end up doing is decomposing those in frequencies and using those frequencies to really try to interpret the data. And those are really the input that we use in our machine learning model. So with those, we can try to interpret what the person is doing. In this specific project, we have this array of electrodes in the sensory motor cortex. So the part that has both the motor and sensory part of the brain. And we're trying to classify different syllables that someone is saying. And it may be odd that we're doing it in the motor part, but and not in the speech part. But you can, as you know, your tongue is going to move differently in your mouth, and your jaw is going to move differently when you're speaking each syllable differently. So we can use the signals from the motor cortex that are controlling those movements to try to classify what syllable was spoken. And here you can see in the brain the array of electrodes, those dots from black to red, and the respective traces of signal in one of those frequency bands are shown under each of the syllables in ba, da, and ga. So we take all of those signals, we put it through both electrodes, frequency, and time, and we put it through an artificial neural network, and we try to get that to predict which syllable the person is trying to speak. And we get pretty good accuracy. For this example, we're getting about 56% accuracy, uh, which is much, much higher than chance, which is less than 2%. You can see some of the confusion matrix here on the right. So on the right, if it was a perfect classifier, you'd see a very black uh, diagonal. The grayish squares around the square around the confusion matrix mean that there were some misclassifications, but it's still pretty strong on that diagonal, meaning that most of those were classified correctly. And mostly of the misclassifications are happening for very similar vowels like fa and va or c and z. And you can think of how we could improve it, especially with the tools that we have in machine learning is, for example, applying a language model on top of that. Not only we're getting what the person is saying, but also we're trying to put that in the context of the English language, for instance, using GPT-3, which is one of the most advanced AI systems out there, to really get the correct phrases out of what someone is trying to say. So there's a full pipeline of what we usually do in these projects. We have these brain recordings from different types of sensors, in this case, ECOGs. We pre-process that data. Here we're decomposing it into different frequencies. We put it into a deep neural network, and we get a classification, and then we can put it in all together, for example, synthesizing that speech for someone that doesn't have the ability to speak, for instance. And maybe it sounds odd. Why would you do that for someone that's already speaking? But for a lot of motor functions, especially, even the act of just imagining that you're doing something will create very similar brain signals to those that when you actually do that action. So either if it's imagining that you're speaking or imagining that you're moving your arm, those same brain regions that would activate if you were actually doing it will do if you're just imagining them. So there's you can do it if you can get those working even if you don't actually do them per se. So another project that we've worked on is trying to decode motor movement with FNIRS. FNIRS now is a less invasive approach. It uses this cap on the right, and FNIRS stands for Functional Near Infrared Spectroscopy. So the idea here is try to measure blood flow in the different parts of the brain, depending on the activity that you're doing. And the system really, it flashes a light through the skull and through this, the scalp. And depending on how much light is reflected back, it can tell how much blood is in each part of the brain. And that correlates really well with activation in the brain itself. In this project, we've been collaborating with academic researchers to develop more of these models, as the way that we're approaching it is very different than what other people do. So it's been really well received in the community. And in particular, we've been working with Dr. Rob Luke in Macquarie University in Australia, who has provided a lot of these data sets for us and has been giving us a lot of insights on how to process it. But here, the person is really trying either tapping their left fingers, the fingers of their left hand together, or the fingers of their right hand. And we're using FNIRS to try to tell what hand the person is trying to use. And again, you can imagine using this as a controller for someone that does not have actual movements of their hand, right? Like as they think about moving their hands, we see those signals in their brain showing up, and we can use those to control a cursor, or we can control anything on a computer screen. And here's an example of how that would look like in the brain. So here is showing oxygenated and deoxygenated blood in different parts of the brain for different activities. So when they're tapping their left finger, we see a lot of blood going to the right side of the brain. and when they are tapping their right fingers, we see a lot of blood in the left side of the brain, which is what you would expect with the way that the brain is connected to the fingers, and that's what we're trying to classify. For this specific project, we designed our own convolutional neural network architecture, and we got accuracies up to 80 to 90% depending on the person. So we were applying this neural network for each person individually, and getting super high accuracy for those participants, which is, as a context, it's much higher than what people have actually been getting with more traditional classifiers, for instance, linear classifiers that are used in the literature a lot more. And another project that we've been working on is this neural latent benchmark. This is really trying to create a sort of ImageNet, the same that ImageNet is for computer vision. It's creating that this data set for neuroscience. So trying to create a set of data set that's very easy to load and to use to start with these neurodecoding algorithms. And it also has a competition, which is similar to a Kaggle competition. And it's the first of its kind. So the first time putting different groups trying to decode the same set of data and see who can get the best accuracies. For this specific data sets, they have actually sensors that are measuring more individual neurons spikes. So we have 137 channels, and the firing rate of each of those neurons. And the idea in this challenge is that we remove some of those neurons, so we hide some of those neurons, and try to predict them, the ones that we hidden, using the ones that we can see. So if we had 100 neurons, we hide 30 of them and try to predict how they were when they were spiking, depending on the other 70 that we can still see. And we have submitted our results, and as of today, we're at the top of the leaderboard. So we have a very cool deep neural network that tries to do exactly that, to predict the firing rate of neurons that were held out, and we got great accuracy and better than all the baselines and the other applications that were there up to this point. So it's really using very good data science and software development here, even though it's a topic that is a lot of people have been investigating for a long time, we've been able to improve upon just using what we already know on data science and neural network models. So a few of the other things that we've been doing at AE that are related to BCI and are super cool to explore is I've been contributing to a lot of open source neuroscience tools. So really trying to get our knowledge in software development and data science development into more of the hands of the scientists that are developing neuroscience tools and using these in actual experiments. We've been doing the same approach of taking original data and original research and applying our models and improving upon them for a bunch of other projects as well. Others with ECOG, for instance, that were decoding arm movement. So we were trying to classify when people were moving their arm and how they were moving their arm based on data from electrodes onto their brain. Trying to classify differences between people either watching something or just listening to something with NIRS data, so that light sensor that we talked about. We've been doing some of this that Sumner has showed you of text decoding, so people imagining that they're handwriting, and we get those signals from individual neurons to try to classify what letter they're writing at each time. And we've been doing some semantic decoding of visual stimulus as well. So people looking at this cloud of words, and with fMRI, we try to create semantics of what they're looking at, and we're really trying to push what the future of BCI is, trying to push what BCI being more uh, increasing human agency and related to effective altruism. So trying to give people control over what they're doing with BCI when we get to the point where this is used through the mass, that we have technologies that we've developed that are easy to use and follow, make sure that all the data that's collected, all the privacy is remained, and the user can trust in the system that they're using. So we really believe that applying uh, correct and good software practices and data science practices that we've been uh, using at AE to BCI projects is really important, and it's going to make a big difference in the future of BCI. So kind of to go over what some of the discussions, so we discussed a lot about neurodecoding, so interpreting those actions from uh, a user and from the brain activity that we're measuring with different technologies, using machine learning that allows us to do that in for a lot of data and in a really fast time. We've been doing that for a variety of different technologies, ECOGs, FNIRS, fMRIs, uh, and the plan is really to expand on everything that the neuroscience field pushes forward. We want to implement and be on top of it to help push the field forward. And we can do that for a variety of different types of intentions. So speaking, movements, visual inputs, audio inputs, um, and always looking at BCI as this really big impact that it's going to have in humanity. And we want to make sure that we have the right technology uh, available for the right people to push it forward. Uh, so we're super excited to go forward with BCIOS, and it's with that I encourage anyone that has interest for projects that are challenging like this, that take a lot of hard thinking and a lot of really trying to push good into these new technologies to apply to work with us here at AE. Uh, and with that, I thank everybody and open to if anybody has any questions.